In linear algebra, we think of a matrix as an action, a machine that takes a vector, stretches it, and rotates it. But functional analysis asks us to step back. We stop looking at the vectors and look at the machines themselves. We treat every possible mathematical transformation as a single point inside an entirely new geometric space. To build this, we start with a normed space, a vector space where every element has a defined length or norm. We then define a linear operator as the mechanism mapping vectors from one normed space to another, preserving their algebraic structure. If we restrict that operator so it can only stretch a vector up to a finite maximum limit, we have a bounded operator. And if that operator compresses a vector all the way down to a single number, a scalar like 5 or -2, it is called a linear functional. Shifting focus from individual vectors to the machines that manipulate them is the prerequisite for navigating higher-level functional analysis. Because you can take two bounded linear operators, add them together, or multiply them by a scalar, they behave exactly like vectors. This means they form their own distinct vector space, which we denote as B of x, y. To give this space a metric, we measure an operator by its maximum stretching power. Look at this unit circle. When an operator acts on it, the circle deforms. The length of the longest resulting axis, the maximum stretch applied to a vector of length 1, is defined as the operator norm. We have a normed space, but is it a complete Banach space? Theorem 2.10-2 states that the space of operators, B of x, y, is complete under one strict condition. The target space, y, must be complete. As a sequence of operators converges toward a final limit operator, the outputs they produce land in y. If y has gaps, the sequence might point to a limit that does not exist. But if y is perfectly solid, those converging operators will successfully form a final valid operator. The origin space X does not matter for completeness. The space of operators inherits its structural integrity entirely from its destination. Now we look at a very specific operator space, the dual space, denoted X prime. This is the space containing all bounded linear functionals, the operators that map vectors from a space X directly down to the real or complex numbers. Because the target spaces here, the real and complex number lines, are perfectly solid without any holes, Theorem 2.10.4 tells us the dual space is always a complete Banach space, even if the origin space X is not. It is tempting to visualize these functionals simply as more vectors living alongside the originals, pointing in different directions. That geometric picture is misleading. A linear functional is much better understood as a topographic math. Instead of an arrow, picture a functional as a dense series of evenly spaced parallel contour lines, or hyperplanes, layered across the space. Under this framework, evaluating the functional f of x becomes a literal measurement. As the vector stretches through the space, the output value is simply the exact number of these parallel hyperplanes that the vector pierces. The dual space is a collection of rulers and gauges. It is a space of measurement tools calibrated to analyze vectors in the original space. We can map out these toolkits for standard spaces. For Euclidean space, Rn, the dual space is simply Rn itself. Every functional is represented by taking the dot product with another vector in that exact same space. For sequences, the mappings shift. If we start with L1, the space of absolutely summable sequences, its dual maps over to L infinity, the space of bounded sequences. This follows a general pattern defined by Holder's inequality. For any sequence space LP, its dual is always LQ, locked in by the relationship where 1 over P plus 1 over Q exactly equals 1. Apply that rule to L2. If P is 2, we set up our equation. 1/2 plus 1 over Q equals 1. Solving for Q gives us exactly 2. This mathematical symmetry means L squared acts as its own dual space. By identifying the specific dual, we generate a mathematically rigorous library of tools uniquely calibrated to measure the sequences in the original space. This visual summary charts our progress. We took mappings and grouped them into the operator space B of x, y. We measured them by their maximum stretch on the unit sphere, and found that their completeness relies entirely on the target space. On the right, we narrowed our focus to the dual space, x prime. By mapping directly to complete numbers, this space of parallel hyperplanes guarantees its own completeness, allowing us to map sequence spaces like L to the P directly to their L to the Q duals. This duality gives us an analytical workaround. When a vector space is too complex to analyze directly, we step outside of it and study the simpler, complete functions that measure it. Understanding dual spaces provides the leverage to solve advanced problems in functional analysis that are otherwise inaccessible within their original geometry.